Okay. Okay, so I hope we can. I hope we can start, right? So it's almost 4. Uh, Hi, everybody. Welcome to this live session for numerical analysis on NPTEL. So I'm the instructor Baskar, and with me our TA Shubham. So we have some participants. We can uh, invite some questions. If you have any questions, you can post it. Meanwhile, I will just summarize what we did in the. Sorry. So meanwhile, I will just summarize what we have covered in the course. We had basically linear systems and numerical linear algebra, where we had linear systems and some methods to capture eigenvalues and eigenvectors. Then we had a chapter on nonlinear equations, where we have learned some iterative methods for single nonlinear equation. And also we have learned to develop numerical methods for nonlinear systems. And then we have learned to approximate a given function by polynomials called interpolating polynomials. We also learned to approximate a function by piecewise polynomial interpolations. Then we went on with some approximations of integrals, integral a to b f of x dx. And then we learned to approximate derivative of a given function at a given point. And finally, we have learned to develop some numerical methods for ordinary differential equations given with an initial condition called initial value problem. We also learned to develop methods for 2-point boundary value problems. So this is the overall summary of what we have covered in this course. So we started with what is mean by Taylor's expansion, because that is, like you would have seen, that Taylor expansion is used everywhere in our course. Of course, other than the linear algebra part, we have also learned how arithmetic errors, that is more precisely rounding errors, can propagate into our computation, and it can magnify or amplify the error in our solutions. So the first part of the course mainly focused on numerical linear algebra. Before that, we had a chapter on rounding errors, which we call arithmetic errors, where we learned stable, unstable computation of or evaluation of a function and so on. And then we learned some exact methods for linear systems. Yeah. So nice to hear from Ravi Shankar. Hi, Ravi. I'm just summarizing what we are doing, but we are more interested to invite some of your questions, and we are here to have a live interaction with you uh, to answer your questions. Uh, so please, if you have any questions, you can ask, and that will be given priority. I'll be generally talking just instead of just waiting for your question. I'm just summarizing the topics that we have covered. But I request you to ask questions. That is more important. So meanwhile, I will just summarize what we were doing. But as I told, the preference is given for your questions. Once your question comes, I will immediately start answering your questions. Okay, so basically we have covered in the direct methods for linear systems. We have covered the Gaussian elimination method with partial pivoting, and we have also covered some LU factorizations. So in this, we have covered Doolittle, Prout, and Cholesky's factorization. And then we have also learned matrix norms. In that, the important concept to concentrate is the subordinate matrix norms. Okay, so given vector norm, what is the corresponding matrix norm? If you are given a matrix and if you are asked to compute the subordinate matrix norm corresponding to say L infinity norm or L1 norm or L2 norm, you should know how to compute that. There are formulas we have given for subordinate norms. These three norms, L infinity, L1, and L2, these three norms, you have given this corresponding subordinate norms formula. You have to probably remember those formulas. Okay. We have also proved three basic properties of subordinate norms. Suppose if you are given a norm and asked whether it can be a subordinate norm to some vector norm, you have to, one good way to see is that whether it satisfies all the three conditions. Okay. If it doesn't satisfy any of the given three conditions, if you recall, we have proved three conditions. If a matrix norm is a subordinate norm, it will certainly satisfy three conditions. That is, if a given matrix norm, we don't know by just looking at the matrix norm, we will not be able to say, yes, it is subordinate to some vector norm. But what you can say is, if that matrix norm violates some one of these three properties, you can surely say that it cannot be a subordinate norm to any of the given vector norms. So that much you can say. Okay. So therefore, if you come across a question where people ask, okay, this is the matrix norm, can you say it is subordinate to any vector norm? You check one of these three conditions. If any one of these three conditions is violated, then you can just close your eyes and say that it cannot be subordinate to any vector norms. Okay. Okay. So mathematics kingdom. Okay. Nice. Yeah, so you are asking in exam, subjective questions will also come. Yeah, so there is no subjective questions. All questions are objective questions. Yeah, so including numerical answer type. Okay, so we have numerical answer type exact, and then numerical answer type which gives a range, and then if you have to give only one single number. Okay, so you cannot give any more than one number. You have to give one single number, but if that lies in a range, then your question is correct. That kind of questions are there, and of course multiple choice and multiple selection answers are also there. Okay, programming part, if you ask, you don't need to write programs. There are very few questions where we will give you a program, either we will ask you to tell what is the output of that program, or we will give a program and ask what exactly, what method that you learned is implemented by this program. You can just go through the program, you see what is the code formula which is packed in that program, right? So by looking at the formula, you can judge that yes, this program is actually implementing this method, that method, like that. Okay, so these kind of questions are there. Okay. Very few. Okay, otherwise we will not ask you to write any program, and in particular there is no subjective question at all, right? So okay, so I hope your questions are answered. Okay, so then coming to our usual discussion. So that's all about the subordinate norms. Okay. Then when you go to the next topic, as an application of the subordinate norms, we have defined condition number of a matrix. Okay. Condition number of a matrix is very important in the theory of linear systems and so on, because condition number of a matrix will tell how sensitive that matrix is to errors when you go to implement any method with that, which involves that matrix, okay, on a computer especially. Therefore, condition number is very important, and condition number depends on what subordinate matrix norm you use, okay. So, therefore, you should know how to compute condition number of a given matrix given a vector norm, okay. So if I give you a vector norm and ask you what is the condition number of so and so matrix with respect to that vector norm, then you have to take the corresponding subordinate norm and compute the condition number. Yeah. So again, there is a question from mathematics kingdom. So what is the difficulty level of the question? Okay, so it's like assignment questions which we are doing are more difficult. So difficult level is fair, I will say, but it's better to say that it's very difficult so that you will learn more seriously and more deeply, right? So therefore, I can say that the difficulty level is more. Okay, but as far as possible, I hope I have followed the norms of NPTEL, which gives good amount of weightage on assignments. I think out of 50 questions, I think 15 questions are coming from assignments. Okay, it's like directly taken from assignment. So if you solve all the assignment problems, okay, maybe when you are submitting, it may be wrong, but later we are giving you solutions, right? So you can not only just look at the solution, you also try to think how this solution is framed and how a similar question is asked, how to write the solution for that question. You frame your own questions. Okay, the best way to learn a subject is not to solve the problem, but to design a problem. Okay? So that's more tricky than solving. Of course, solving is more difficult, but if you try to make questions, okay, suppose you have a concept, okay, you think what are the possible questions that you can frame. That itself will take you to a deeper understanding of the problem. Okay, so you look at the assignment problems and try to think what are the possible questions that can be asked, which are fitting into the theory behind those problems. Okay, and try to solve. Once you frame the question, you can solve them, right? So you go through all the assignment problems, try to solve them because there is a good amount of weightage. And then we have some 10 questions which are more or less directly taken from the theory. Okay. Like we may just give a formula and ask what is this formula. Okay. Or we may just give a method and ask what is that formula. Okay. Of course, such questions can be only multi MCQs or MSQs, right? Then we will give you say some matrix and ask whether so and so method can be applied to this and this kind of questions. Okay, this kind of questions which are like if you have followed all the videos or and you have read the notes that we have given every week, then there should not be any problem in just attending those 10 problems. So there are 10 problems which are testing your class material, including video and notes. 15 marks are directly taken from the assignments. And there are, of course, 25 questions which are something which you have not seen in assignment, or perhaps in notes you would have seen them, okay, but definitely not exactly taken from the assignment. But ideas will be there. See, you cannot go out of the syllabus and frame a question. That's not possible, right? So therefore, whatever we frame will be within what we discussed in the class and assignment only, but it will not be exactly taken from the assignments. Okay? The such questions are there, 25 questions. Okay. So Ravi Shankar is asking, Rangikuta method. Yeah, and for first order, second order differential equations. Rangikuta method is mainly introduced in our course for first order initial value problems only. Therefore, you don't need to worry about the Rangikuta method of any other problem other than what we discussed in the class. Okay. So we have discussed Rangikuta method of order 2. That is more important. Order 4 is quite lengthy to compute, but nevertheless, you may have to just remember the formula. See, since we have not derived the Rangikuta method of order 4, you perhaps have to remember it. Okay, Rangikuta method of order 2 is very simple formula works. Okay, so these are the two method that we will ask, and that is only for the first order equations. Okay, I hope, I don't know exactly what Ravi Shankar is asking on Rangikuta method, but I hope I tried to answer his question. Okay, so Math Kingdom is asking assignment which are given at the end of each chapter notes after solving it. How will I come to know that my answer is exact? Can we get answer key of that? Okay. So this is one of our students asked sometime before, and since we don't have answer keys at present, so I have to sit and prepare and then post it. Therefore, it may take time. So as of now, we don't have answer keys. I'm very sorry for this. But yeah, so how to know whether you have what you solved is correct or not is something which you can write an email to me so that we can discuss also. Okay. So on email we can discuss. So I will try to make the answer keys for all these problems. Yeah. Yeah. So then we went on with after condition number, we have gone into the iterative methods. We basically introduced two iterative methods, Jacobi method and Gauss-Seidel method. We have also introduced successive over relaxation method for the Gauss-Seidel method. Yeah. Okay. So thanks. Thank you. Successive over relaxation method is based on again Gauss-Seidel method. We have also proved two interesting theorems here. One is the sufficient condition for this iterative method, that is Jacobian Gauss-Seidel, to converge. That is, if your given matrix is diagonally dominant, then your Gauss-Seidel or Jacobi methods for that system will surely converge. Okay, so suppose we give a matrix and we ask whether Jacobi method will converge or not. First thing you see is whether the given matrix is diagonally dominant or not. If it is diagonally dominant, you can just tell, you can write that yes, it will converge. Okay. If it is not diagonally dominant, then don't conclude that it will not converge, because the theorem is only a sufficient condition. Okay, it's not a necessary condition. Therefore, you cannot say that if a given coefficient matrix A is not diagonally dominant, it will not converge. You cannot say that. For that, we had another interesting theorem, which is necessary and sufficient condition for the convergence. That is, in that we have used a notion called spectral radius. Okay, so the spectral radius for the iterative matrix. There is a difference between these two theorems. In the diagonally dominance, that is the sufficient condition, you have to check the diagonal dominance of the coefficient matrix. Okay? Whereas when you go to check the spectral radius, you have to check for the iterative matrix. So first you have to write the iterative matrix of the given linear system for any of these two methods, either Jacobi or Gauss-Seidel. There is a way to write the iterative matrix, then compute the spectral radius for that. If the spectral radius is strictly less than 1, then we'll say that the corresponding iterative method will converge. Okay. So therefore, if I give you a matrix and ask you whether the say Jacobi or Gauss-Seidel converges, then you have to keep these two concepts in mind and check. Okay, and accordingly you have to answer. And SOR method, you have very the two theorems. You just have to understand the statement of the theorems, and then you have to keep them in mind when you are answering any question based on SOR method. Then comes the eigenvalues and eigenvectors computation. Here we have introduced only one method, which is power method. Okay, so in this we have some hypothesis for the power method. You have to be clear about the hypothesis. If you ask whether power method will converge or not, if so, to which eigenvalue it converges. Remember, in usual circumstances, if all the hypothesis of the power method theorem is fulfilled by a given matrix, then and a given initial guess, then the power method sequences tends to the dominant eigenvalue. It should be a unique dominant eigenvalue, and a corresponding eigenvector of the dominant eigenvalue. Okay, so therefore, and there are other reasons for which it may not converge to the dominant, but the next dominant eigenvalue, and so on. Okay, so these are the technical things that you have to learn in the power method. Then we had inverse power method, which is just applying the power method to the inverse of the matrix. Okay, therefore everything goes just the reverse way. It will tend to converge to the smallest eigenvalue, smallest in the absolute sense. That is the inverse power method, and all other ideas are just borrowed from the power method to inverse power method. And then we had some shifted power method also. And that's quite tricky to answer any question. But power method and inverse power method are not that difficult once you understand the statement of the theorem. Okay, where the sequence, if everything goes well, where that sequence converges. There are two sequences generated by the power method. One is a sequence of real numbers, which is supposed to converge to the dominant eigenvalue if all the hypotheses are fulfilled. And there is one more sequence, which is a sequence of vectors where that sequence converges. See, that is inbuilt in the proof of the power method theorem. Okay, so that you have to just go through and keep in mind where that converges. Okay, so that is also important. Then we have discussed a very interesting theorem called Gashgorian theorem. You should know how to construct Gashgorian disks, and you should be able to conclude whether all the eigenvalues are distinct, whether you have dominant eigenvalue for the given matrix through Gashgorian theorem. In a lecture, we have given some examples, interesting examples. If you go through those examples, that itself is enough for you to understand those concepts. Okay. In fact, you can also use Gashgorian theorem to see whether the Jacobi method or Gauss-Seidel method converges. It may not work always, but at least from the examination point of view, we will give you some matrix where it works or it trivially not work. Okay, so this kind of questions only will frame. So you should know how to use Gashgorian theorem to see whether the spectral radius of the iterative matrix is strictly less than 1 or not. Okay, all the examples are given in the class, the lecture, video lectures. Okay, so you can watch that and be clear about that concept. So that ends the chapter on linear algebra, numerical linear algebra. Then when we went on with nonlinear equations, basically we had two types of methods. One is the bracketing method and other is the non-bracketing method. In bracketing method, we have discussed bisection method and regular falsy method. Okay. So bisection method generally, so these two methods will surely converge. That is one good thing, provided if you give an initial interval in which you locate at least one root. Okay, so there's a way to locate, right? So you have to see the sign change of the function f, which defines the nonlinear equation. Okay, so and then once you are given an interval, then you can go on bisecting the interval at every iteration and then check for the sign change, which part of the interval changes its sign, and then you will take that part and leave the other part. That's the bisection method idea. A regular falsy is that you will just connect the secant line between these two endpoints of the interval and see where it intersects the x-axis. Okay, so these are the ways that you will construct the iterations in regular falsy method. Otherwise, the idea of bisection method goes exactly with the regular falsy method. Only thing is how you will divide the interval into two parts. That's the only difference. Okay, and then just a small algorithmic correction of regular falsy method will lead to secant method. It's a open domain method or non-bracketing method. And then we have also learned Newton-Raphson method and then fixed point iteration method. Okay, so these are the methods we learned in nonlinear equations. In this, you should also carefully see that bisection method and the fixed point iteration method. These two methods have a nice feature that suppose I want to get my root approximated with certain absolute error. Okay, suppose R is my root and I want to compute my iteration up to a n such that xn minus r modulus should be less than some number, say 10 to the power of minus 5, minus 10, something if we give. How many iterations I have to perform? Okay, one way to understand this is to perform it on a computer and see, right? For whatever n, if you have mod r minus xn is less than that epsilon that you have taken, then you stop the iteration. Okay? The other way to know that n and the number of iteration needed is to go for some very interesting estimates which we have discussed in those classes. Okay, so such estimates are there for bisection method and fixed point iteration method. So you should carefully go through that and understand it. Otherwise, you should also know what is the order of by a Newton-Raphson method, what is the order of secant method, and so on. Okay. And then if I give you an equation and ask you whether Newton-Raphson method will converge quadratically or not. So when to conclude such things. Okay. So these all are discussed in the class, so you have to go to these are important things. And of course, if I give you x naught and a method, you should be able to compute few iterations. Okay, so for that you may have to also remember those formulas. There are only basically two formulas: secant method and Newton's method, right? They have a very rich geometric idea behind them, so you don't need to really memorize them. You just if you understand the geometry of them, they are very intuitive, and therefore it is very difficult for you to forget those formulas once you understand the geometry behind them. Okay, so that's the nice part of these two methods. Other than that, everything else is quite intuitive. Okay, so the next part of the our course is on this one, yeah, so just the good. So there are 13 viewers. See, I'm just summarizing, but what is important is if you have questions, you please ask so that you can get more ideas and more clarity on the subject. Okay, so therefore, don't think that I am talking, so you should not disturb. I'm just talking because you are not asking questions. Okay, so the first preference is to answer your questions. Okay, so please ask questions so that it's more interesting for us to discuss. Okay, otherwise, I'll be generally recalling what we did. Okay, so the next chapter is on polynomial interpolation. So here we had, yes, okay, so PDE lover, very good. Okay. Okay, from examination point of view. Okay, thank you, thank you. So therefore, you prefer to listen to me than asking question, I guess. Huh? Okay, that's nice. Then if I want you to ask question, then I should not summarize. Huh? That's the good. Okay. Okay, please ask questions. So I'm just instead of quietly sitting, I'm just talking something. Okay, so it's more important for me to answer your questions, and that's the main purpose of the live session also. Okay, nice. Now, so coming to the interpolation, polynomial interpolations. You see, first thing we should understand is for a given data set, you have a unique interpolating polynomial. Okay, that is the first point to keep in mind. And there are two ways that you can construct this polynomial interpolations. Basically, one is a Lagrange way, and another is the Newton's way of interpolating polynomials. Okay, these are very basic interpolating polynomials. So there are more sophisticated interpolating polynomials. For instance, you not only want the interpolating condition, you also want certain smoothness at the node points. Okay, then you have to go for say Hermite polynomial, Hermite interpolating polynomials. We only considered Hermite interpolating polynomial with 1 degree of smoothness. That's all. Okay, you can also go for higher degree of smoothness. And similarly, we also introduced for piecewise polynomial interpolations. Okay, if you just go with piecewise Lagrange form or equivalently Newton's form, you will always have the problem of not having smoothness at the nodes. Okay, they are only continuous. Piecewise polynomials in the Lagrange or Newton sense is only continuous but not differentiable at the nodes. Okay, so this is the main reason for why we have to think about some more sophisticated ideas like Hermite polynomials. Okay, and also we introduce plane interpolations. Okay, so you have to recall what is Hermite polynomial, how to construct Hermite polynomial, and so on. Similarly, how to construct Lagrange polynomial, Newton's interpolating polynomial. Then in Newton's, we also have an important concept called divided differences, right? So if I give you a function and nodes, you should know how to construct the divided difference of that function of whatever order we give. There are some nice properties of divided differences. One is that it is symmetric. Okay, that you have to keep in mind. Okay, so people can make many tricky questions out of that. Okay, so it's a symmetric means what? What it mean by the divided difference is symmetric with respect to its position of the nodes. Okay, so this you have to keep in mind. And of course, you have to know the definition of the divided difference. Okay, so divided difference of a given interpolating polynomial of degree, say, n. What is the definition? How it comes from that polynomial? Okay, it's a basic definition. And there is also a formula to compute it. In fact, we have introduced two formulas. One is the basic formula. Another is using Hermite-Ginocchi formula. So Hermite-Ginocchi formula is, well, it is equivalent to the basic formula, but it also goes beyond the purpose of divided difference from the interpolation point of view. See, in interpolation, we always consider nodes to be distinct. But in the later part of the course, like when you go to the quadrature formulas and all, you may have to come across a situation where the nodes sometimes may coincide. Okay, so in such cases, you need to still give the meaning for the divided differences. Okay, for that we have established another formula called Hermite-Ginocchi formula. Okay. So these are very important. What is finally important from the Ginocchi formula is that there are certain properties that can be derived from them. Okay, so there is a question from mathematics kingdom. Somewhere in lecture notes where closed intervals are given throughout the proof of the theorem, but in lecture you took semi open interval while proving the theorem. Yeah, these kind of, it should not be a confusion because I may be taking it for certain other reasons. So in such cases, what maybe that it doesn't matter whether you work with the closed interval or open interval or semi-closed open interval. Okay. So your basic theorems may support everything. Therefore, I may just use it for the convenience. Okay. So if you pinpoint and tell me where we did, then say for instance, Rolle's theorem. See, you want the you want to use the Rolle's theorem to have somewhere in between. See, suppose you have f of a equal to f of b. Okay. Then what you will say is you will say that there exists xi such that f dash of xi is equal to 0, right? Uh, so where that xi belongs to? Okay, if you ask, if your function f is a constant function, then also f of a equal to f of b, right? It's a constant function, and f dash is 0 for all x in that case. Therefore, that xi can be a or b also, right? But often it's sometimes what happens is we will put open interval because we don't want the xi to be captured on the boundaries for certain reasons in the proof of that particular method or something. So then what we will do is anyway basic theorem supports anything. So I will just say open interval. Sometimes one particular side of the interval I don't want to include in my proof. Okay. So I will use semi-open interval in that case. Okay. Similarly, when we use mean value theorem, we have certain freedom to choose. Okay. So it depends on what we want, actually. Yeah. So that is, so if you pinpoint and tell me where we did, we can say why I took like that. Okay. So in that case, I think you should not get confused. You should look whether things will go on with closed interval or open closed interval also. Then you see you have the flexibility of using that. Okay. So if you just pinpoint and give me, then probably we can avoid that confusion later in the later versions. Okay. See, many times what happens is when I prepare the slides, I may not consult the notes. Okay. See, that is the problem also if we know too much about that particular theory. So we don't make the slides by looking at the notes. So then there may be a difference in the discussions between these two. Okay, so this is perhaps why such things came. Okay. 30 to 40, 40 to 50, 50 to 60. Okay, so Ravi Shankar is asking some question. Using Newton's forward interpolation, which limits we take in cumulative? Oh, so I don't understand this question. See, in as far as the Newton's interpolation is concerned, we have used only central difference. Okay, central interpolation. We can also similarly go for forward or backward interpolations, but we have not discussed it in our course. Okay. So therefore, you can, from our course point of view, you can just need not worry about this. But which limit we take in cumulative? I don't understand your question. Maybe you can put it more clearly. And then we can try to see what you are exactly asking. Okay. Okay. So continuing our discussion on summarizing the things, then we went into quadrature formulas. In quadrature formulas, we have discussed two ways of constructing quadrature formulas. One is using interpolating polynomials, like you approximate your function by interpolating polynomial and then integrate it. And that is also called Newton's code formula. And another one is a method of undetermined code. So everything is in Newton's code formula. Okay, you can also derive Newton code formula using method of undetermined coefficients. Here there are two approaches. One is You give the nodes and ask only the weights. Another is don't give the nodes as well as weights. You have to compute both. Okay, obtain both from the by solving a nonlinear system. So the second one is actually the Gaussian quadrature formula. The first one, where the nodes are given and you have to only find weights. These are generally, it's a particular case of Newton code formula. So we had a rectangle rule, midpoint rule, trapezoidal, and Simpson in the first type. Okay, so you have to also learn to also see their what is called the applying them to the piecewise form, which is called composite rules. Okay, so their error formulas are also derived, not for all, but Simpson we have not derived, but we derived for other things. Okay, so and when it comes to Gaussian quadrature formula, we have derived only the Gaussian quadrature formula for n equal to 0, which will be the same as the midpoint rule, and n is equal to 1, we have derived. Okay, and for derivation, we have only taken the interval -1 to 1, but later you can always transform it to any interval a comma b. Okay, so that one has to keep in mind when you are solving problems using Gaussian quadrature formula. Okay, then we went to numerical differentiation. Yeah, see, we have again, so you are worried about what we have not covered. Ravi Shankar is asking maybe he's asking how to derive the error formula for Simpson's method. Okay, see, error formula for Simpson's method is little tricky than trapezoidal and rectangle. Okay, so the Chebyshev nodes. You see, this is not very difficult for you to remember Chebyshev. Okay. Yeah, I cannot say whether. So I'll prefer to say that yes, you learn Chebyshev nodes, and you see, it's not very difficult, I think, to remember Chebyshev nodes. Okay, therefore. I advise you to learn that. Okay. Coming to Simpson's error formula, we have not derived in the class, but I think in the notes we have given the derivation. But it is little tricky because it is important. See, Chebyshev notes are very, very important from the practical applications because they are kind of gives better approximation than Lagrange form. Okay, therefore they are really important. So it's nice to once learn. Of course, when you go to apply them practically, you don't need to remember them. But at least once for the examination point of view, you can just remember it. Okay. So coming to again Simpson's error formula derivation, why it is difficult is because if you recall the derivation of the error formulas for quadrature rules, we mainly use the mean value theorem for integration. Okay, mean value theorem for integration demands that one of the functions in the integrand, which appears as product of two functions, they both should be continuous, but one of them should not have sign change in the interval. It should be either negative or positive. Okay. So in trapezoidal rule and rectangle rule, it comes very nicely. Therefore, you can directly apply the mean value theorem for integration, as you would have seen in the class. Okay. But in Simpson's method, it's not the case. Okay. So it has to change sign. And when it changes the sign, then you have to slightly modify the integrand. And then apply the mean value theorem for integration. So that's quite tricky, and you have to also use the Hermite-Guinocci formula there to finally arrive uh, at the formula, the error formula. So this is little tricky. Therefore, it's a first course, so we omitted the proof of that. The same idea will go for any kind of Simpson's method. Therefore, it's interesting to learn it as a knowledge. We have given that proof, I think, in the notes. But from the examination point of view, we will not give any weightage for the proof of that theorem. Also, however, you may have to remember the error formula for Simpson's method.
There's a question.
Mathematics kingdom. So he's asking, while proving error in rectangle rule, we took the interval AB, but in the notes. Yeah, so here it doesn't matter. Why we took the interval, open interval AB is that we want that function G to be strictly greater than 0. Okay. Just I was talking about the Simpson's error derivation. You know, when you go to apply the mean value theorem of integration, you just have to make sure that as I told you, the integrand will appear as a product of two functions. One of that function is strictly greater than 0. It's not very important because, you know, if you include a, it will be greater than or equal to 0. But including one point in an integral makes no difference as far as the integral is concerned. Okay, therefore it's not so important. That is why perhaps I just left the point A there. Okay, you can also include that. Then it will become a greater than or equal to 0. Then student may get confused that how can I apply mean value theorem for integration? Even then it's not a problem. But then I just put that excluded that point A just to make that one of this integrand to be strictly perfect. Okay, so I think this is, you need not worry about that. That one point excluding will not make any difference in as far as the study of integration is concerned. Okay, I hope this is okay. Happens while proving error in trapezoid. Same idea. See, in excluding A, it will not make sense. It's just one point, and you know, your integration will not care even if you exclude a set of points, which the set is in fact countable. It doesn't matter, right? So this is just one point, so it doesn't matter for you. It is just for the convenience to show that all the hypotheses which we stated in the notes are well satisfied by the integrands which are sitting in the expression for the derivation of the error. Okay, and that it doesn't matter. Okay, Ravi Shankar is asking Euler and Euler modified methods. Okay, so again, I don't know what is the question behind that, but Euler method, we have introduced two form of Euler method. One is forward Euler method and other is backward Euler method. Initially, we introduced these two methods as explicit methods, just to have. So suppose if I give you x naught and ask you to find the solution for any x which is greater than x naught, then you have to go to use the forward Euler method. If I ask you to get the solution or approximate the solution using Euler method for any x which is less than x naught, then the idea is to go for backward Euler method. So that is what is a tricky point in Euler's method. And in Euler modified methods, we basically had two methods. One is the midpoint rule, and another one is the trapezoidal method, midpoint method and trapezoidal method. In trapezoidal method is an implicit method. So there we have also introduced a predictor corrector approach. Okay, so these are some of the important things that you have to remember. And then we had gone into multi-step methods, and also in one-step method we had higher order methods like Rangikuta method. And so these are the things which are covered in the last week, right? So mathematics kingdom is asking, but somewhere you took greater than equal to 0. Yeah, so yeah, so that you see, finally this in this particular theorem, that is the error formula, it won't make any significant change. Okay, so I just excluded A, thinking that it may confuse you, because then it becomes that one function will become greater than or equal to 0. So, but I might have forgotten to remove it everywhere. Okay? So I'm sorry for this confusion, but it doesn't matter for you. Okay, so one point, if you remove A, that function will become strictly greater than. If you don't remove A, it will be greater than or equal to. Either way, you can go ahead with the theorem. Okay, so I just try to remove A to make it strictly greater so that it nicely matches with the mean value theorem of integration that we stated. But then I would have forgotten to remove everywhere greater than or equal to when I was preparing the slides. Okay, I'm sorry for this error, but I will try to correct it in the next time. But mathematically, you need not get confused because both ways it will go on. Okay. Okay, so PD lover is asking, okay, theorem, yeah, so second mean value, oh, I see, okay, so it is greater than or equal to only is written in the theorem, is it? Oh, I'm sorry, so then I might have unnecessarily confused you this, okay? I'm very sorry for this, okay? I was somehow thinking that it is strictly greater than. So I would have just retained closed interval AB then. Okay, so that so thanks for bringing this error to my notice. So I will correct it next time. Okay. Yeah. So therefore, yeah. So I was under the impression that it was greater than. So I just made it greater than by excluding A. Okay, but that was an unnecessary exercise. Either way, just removing one point should not matter. I should have kept it. Yeah. So then in the final week, we had some multi-step method. As I told, we have introduced Euler method in the 11th week, and then in the 12th week we have also introduced the Rangikuta method of order 2 and 4. They are higher order methods. Okay, so that's very interesting, and one-step explicit methods. Then we have introduced the implicit methods and multi-step methods. There are two approaches here. One is Adams' approach, and the other one is some backward differentiation formula. We have only covered Adams' approach. We have just given an illustration of how to derive these methods. Okay, so as you go on with multi-step methods, it's more and more difficult for you to derive them. Okay, so we just illustrated it with three-step method. There are two types of methods that you can derive in the Adams framework. One is the explicit methods, which are called Adam-Bashforth method, and another is Adams-Muller method, which are implicit methods. Okay, so why all these complications? Then comes, okay, so you have Euler method, you have Rangikuta method, which is a higher order method, explicit method. When these are there, why we have to go for such complicated Adams ideas? This is because in certain applications we have stiff problems. Stiff means one aspect of stiff problems is that your solution can change rapidly in a small interval. Okay, Explicit methods, generally speaking, they struggle to capture this kind of stiff phenomena. Okay, whereas implicit methods are more capable and more efficient in the sense that you don't need to really give a very small step size. Okay, we have illustrated this with Euler method, and also we have shown how these are drastically improved in implicit methods by illustrating this phenomena with trapezoidal method, because these are the most simple version of more complicated class of Adams methods. So we have just illustrated them with these two methods, and these are basic idea of stability analysis. And then we went on with this boundary value problems, 2-point boundary value problems, where we first considered linear boundary value problems. We have introduced central difference methods for linear boundary value problems. And then we have also introduced a shooting method, okay, for nonlinear 2-point boundary value problems. Okay. And this is a little confusing. Shooting method is little confusing because you have to first define a second order initial value problem, and by changing certain parameters in this initial value problems, you will try to iteratively approach the solution of the given boundary value problem. Okay, so that's a little looks difficult, but it is not very difficult once you understand it. Okay, so that's very important. Shooting method, it's very nice and interesting method, therefore you have to pay more attention and understand it. These are the overall idea of what we covered in our course. So I hope you enjoyed this course, and if I have made some errors like what you have, what made you to get confused, I'm very sorry for this. We will also try to improve this material as we go with next versions and so on. So I hope you have enjoyed and you have learned numerical analysis to a nice and a nice, interesting way. So thank you for all your patience and support, and also my best wishes for your exams. So you have any questions, you can ask me. Yeah, thank you very much. So also thanks for Shubham sir and Nitin sir. Okay, good. Okay, looking forward to numerical differentiation. Yeah, sure, we will do that. Okay, so in the coming years, we will do that. Okay, thank you very much for your support. Yeah. So any questions? Okay, so it's time is up. So let's sign off. Thank you very much for your patience. You have listened to me, asked many questions. Thank you very much for all this. And yeah, see you. Bye. Yeah, thank you very much. This one, huh?